Surds. We've been talking about irrational numbers. Probably the most common one we deal with are surds. And a surd is simply any number that includes a radical symbol. In case you're unaware, a radical symbol is that square root sign. Like that. And can't be calculated exactly. So, for instance, the square root of 9 is not a surd because we can calculate that exactly. So ones that we cannot. It doesn't have to be a square root. It could be a cubed root, a fourth root, a fifth root. If we can't work it out, it is a surd. So some surd laws that allow us to manipulate these numbers. Because what we're basically saying is a surd is an unknown. Well, algebra is all about unknowns. So a lot of the rules we have for surds are exactly the same as algebra because we're doing exactly the same thing. We're adding unknowns and multiplying unknowns and things like that. Although we can manipulate them a little bit. This is the rule that allows us to simplify surds because the square root of a times the square root of b will be the square root of ab. If we can make one of those factors a perfect square, then we can simplify the surd. Similarly with division, guess what this one's saying is, hey, you get the square root of a fraction. If you can work out the top or the bottom, we'll do it and just leave the surd on the other side. This one's a little bit obvious. But if you square a square root, then they cancel, if you like. They're opposites or inverse operations. So they will cancel each other out and left with the a. So let's look at some. So the idea being, okay, there's the square root of 50. I'm looking for the biggest perfect square that will go in a 50, and that is, of course, 25. In our head, we probably don't write this down. We go, okay, well, that's the same as saying the square root of 25 times the square root of 2. The square root of 25 is, of course, 5. So we get 5 root 2. So that is the idea of simplifying a surd. We saw this one with algebra, remember. Square root of x cubed. Using this idea, I can say, oh, well, I can write it as a perfect square, because a perfect square would be x squared times x. Square root of x squared is x root x. But remember, the easiest way is to put it back in the index form and think about it, well, x to the power of 3 on 2, we can think about that as 1 and a half. So it's x to the power of 1 times x to the power of a half. Root 5 on 4. Well, I don't know the square root of 5, but I do know the square root of 4. So I can tidy that one up, root 5 on 2. Root 20 on 9. So again, I do know the square root of 9, but also the square root of 20 can be simplified because there is a perfect square that goes into 20, that of course being 4. So 2 root 5 over 3. Surd arithmetic. That is exactly the same as I wrote down now, very first lesson. The only difference is I've written the word surd instead of terms. And it's like I was saying, a surd is an unknown. An algebraic term is an unknown, so the rules are exactly the same. So I get something like this, 4 root 3 plus 6 root 2 minus root 3 plus 2 root 2. Look, I don't know what the square root of 3 is, but I do know that if I have 4 of them and I take away one of them, then I've got 3 of them. Still don't know what they are, but I know I've got 3 of them. So just like algebra, we can simplify that. 3 root 3 plus 8 root 2. Binomial expansion. First outside, inside, last. Okay, so in this case, nothing simplifies down, so I'll just leave it like that. 18 plus 3 root 3, 6 root 2, and root 6. Difference of 2 squares. So that's just going to be, oh look, conjugate surds. Conjugate surds is when you've got the same numbers, but the sign in the middle is different. The classic question which allows you to do the difference of 2 squares, in this case 2 minus 1. Of course, the most common mistake for this question would be, what do you reckon? 3. Because people go, square root of 2 times square root of 2, oh, that's 4. And they write 4 minus 1 is 3. Classic mistake, happens a lot. Perfect square. First one squared, twice the middle, last one squared. And 4 plus 2 is, of course, 6. So all those same operations that we saw in algebra appear in surds as well. Okay, we'll have a go at 2C.